So this video is about something called principal coordinate analysis. So far in multidimensional scaling, we've seen the case where we're given a distance matrix D and we are asked to find a set of points with distance matrix that is approximately equal to D or is equal to D. Okay. So principal coordinate analysis does exactly the same thing, okay, but sometimes we have the data to start with. Okay. So suppose we've got a bunch of data points x1 to xn with distance matrix D, and the x's are in some high dimensional space Rp. Then can we find a set of vectors y1 to yn in a lower dimensional space Rk that have a distance matrix approximately equal to D? Or more generally, we can express this as an optimization problem. We want to find the vectors y1 to yn to minimize the difference, the squared difference between the distance matrix elements dij and the distance between yi and yj. And here d might be Euclidean distance. It might not be Euclidean distance. It might be something else. Okay. So far, we've focused on multidimensional scaling, classical multidimensional scaling. And what classical multidimensional scaling, the optimization that problem solves is slightly different. It still tries to find points y1 to yn in some lower dimensional space Rk, but now it's trying to minimize the difference between the centered inner product matrix B and the inner products between yi and yj. So that's the problem we're solving in classical multidimensional scaling. We're trying to find a vector y which is an n by k matrix such that y transpose y is approximately equal to the centered inner product matrix of the data B. Well, how do we measure that? Well, this sum here, if you think back to the chapter on chapter 3 where we looked at matrix norms, this is just the Frobenius norm between B and y transposed. Sorry, I got this wrong here, didn't I? This should have been y transposed, yeah, because y has as rows the vectors y1 transposed down to yn transposed. Okay, so you want to find a matrix y so that y transposed is approximately equal to B, and this is equal to the Frobenius norm squared. That was the definition of the Frobenius norm. Well, if y is an n by k matrix, then y transposed is a rank k matrix because it's just a linear combination of the k columns of y. And so we know something about this. We're trying to approximate B here by a rank k matrix. And we know the optimal choice here. So if B has spectral decomposition U lambda U transposed, then we know that the optimal rank K approximation to B is BK, which is UK lambda K UK transposed, where UK is the first K columns of U. Okay. So this is by the Eckart-Young theorem. Now then, let's let Y be UR times the square root of the matrix lambda K. Okay, so lambda K here is the diagonal matrix of the eigenvectors lambda 1 up to lambda k. Then we've got that y transposed is bk. Okay, so we know that y, which is ur lambda, sorry, that should have been uk lambda k to the half, is a set of points. So this is a matrix, which is n by k, it's a set of points in k dimensions that gives the best approximation to B. Okay, we've got y transposed is B. So these are known, these are called the principal coordinates of the data. So to summarize, we've said that for classical multidimensional scaling, the problem that we're trying to solve is to find coordinates, points y in some space Rk, such that their centered inner product matrix, or their inner product matrix, because that means 0, is approximately B. And the way we do this is via truncating the spectral decomposition here. So this is starting to sound a lot like principal component analysis, right? In fact, this is very similar to what we did in PCA. So let's just comment on that. Okay, so let's suppose we've got given a data matrix X, which is n times p, okay, with distance matrix D, which is n by n. So just recall what PCA does. PCA takes the centered data matrix Hx and it finds the singular value decomposition of this, U sigma V transposed. The first k principal component scores are yk, which is uk sigma k. Well, what does multidimensional scaling do? How does that compare? So this forms the centered gram matrix B, which is hx transposed. Now, if we substitute in the singular value decomposition of hx, what we're going to get here, we're going to get that this is u sigma squared u transposed. Okay, or we'll call this u lambda u transposed, where lambda is sigma squared. This is its eigen decomposition, its spectral decomposition. Then the principal coordinates we said would be y k is u k lambda k to the half, which is u k sigma. That's exactly the same as we found for PCA. So let's have a proposition just to state this. Okay. So let's say if X is an n by p matrix of Euclidean distance matrix D, then the PC scores based on the first k principal components equal the k principal coordinates based on D. So principal component analysis, when used to find principal component scores, is doing the same as classical multidimensional scaling. Okay, they're doing the same thing.